Alrighty. Well, welcome back, everybody, to another edition of our Zoom Talk series. I hope you all have had a good day. Today, our guest speaker is Dr. Kathy Kornei. She's been an astronomer her entire life, and she's really an astronomer, but she's also a science writer as well. As she has published work in so many different places, namely also, you have Scientific American, New York Times, but plenty of others as well. She got her Bachelor's of Science at Yale, and she got her Master's of Science and a PhD at UCLA. Is that correct? Yeah, I think so.
That is correct.
And with that introduction, I'll leave it to you to do your talk on our solar system and others.
Great. Well, thank you again for having me. I'm super excited to chat with you. I would love to obviously chat astronomy, but we can also chat careers, anything that might be helpful to you in terms of what you're considering for the future. So yes, as was mentioned, I'm trained as an astronomer. So spent a long time in school studying it, 4 years of undergrad, 6 more years of grad school. So full 10 years doing that. I was using some of the telescopes out in Hawaii, which was really amazing to go out there. These are the massive, massive telescopes where the mirrors are measured in meters, not centimeters. So it was really cool to do that kind of research. Went to a lot of conferences, met a lot of other astronomers, presented my work. And after grad school, I realized that I loved sharing science with people who weren't necessarily PhD scientists. So I loved communicating science to the public. And that was what really drew me into working as a journalist. So now what I do is I take the very technical information that the scientists give me, and I break that down and I make it more approachable. I make it hopefully more interesting, something that a member of the public can really understand and grasp and kind of get at why science is cool and why we should keep funding science. So that's what I do now. And I write about astronomy somewhat, but I also write a lot about earth science. So I do everything from glaciers to oceans to ice, everything and everything. It's been a lot of fun and I've learned a ton. So what I want to do today is we're going to do something hands-on to get us started. We're going to start thinking about solar systems. So piece of receipt paper. I think most people hopefully have one. Should be a meter long-ish. Doesn't really matter. Somewhere around there. So we're going to do a little bit of folding. And the purpose here is we're going to chat about our own solar system, but we're also going to talk a little bit about how other solar systems look different, which I think is really interesting, that, ours is definitely not run of the mill in terms of what we're seeing out there. So start with your piece of paper, grab a pen or a pencil. And at one end, you're going to want to label it sun. So we're going to label our endpoints of the solar system. We're going to have the sun at one end, and then all the way across. You're going to label Kuiper belts on the other. So that's bracketing the ends of the solar system. You can make a sketch if you want, or you can just write the words sun and Kuiper belt. All right. And of course, there's some debate in terms of what is the actual end of the solar system. We're just adopting the Kuiper belt here. But the Kuiper belt itself is kind of this, it's very broad. It's obviously not one particular point in space. So a little bit of imagination here in terms of what is the actual end point. So now take your piece of paper, fold it together end to end, and make a crease in the middle. And open it back up. So what object in the solar system do you think is roughly the geographic middle between the sun and the Kuiper belt? I'm open to all guesses.
Saturn, perhaps?
Saturn? Any other guesses?
That's honestly what I was going to say.
Yeah?
I think it's probably further up than Saturn. My guess is going to be like Pluto.
Pluto, okay.
I was gonna take a way out guess because I know this solar system is really big. Maybe the Oort cloud, or wait, that's even further
So
away.
that's even beyond the Kuiper belt.
Yeah. Okay. Never mind. Scratch that.
So it's actually something that has not yet been named. It is the planet Uranus. Uranus is roughly the middle. So go ahead and either sketch, draw, label. And that's going to be our midpoint. We're going to work from that. So our next task here is we're going to take our Kuiper belt end and the Uranus, the line that we drew for Uranus, and fold those two together. So you get a loop. And then make a crease at this end. And then open back up. That crease that you just drew, we have something between Uranus and the Kuiper belts. What would that be? What planet do we still have lurking out there?
I'm guessing Pluto again.
Oh, good guess. What else do we have out there other than Pluto?
Neptune.
Neptune. Bingo. This is Neptune. We're now going to work from the sun end. So hold the sun end, and you're going to fold that to Uranus. So again, another loop. And make a crease. Any guesses as to what planet we're going to put there?
Mars.
Mars? Any
Jupiter.
other guesses? Jupiter? Something else big, some other big planet.
Saturn.
Saturn. Bingo. This is our ring planet. So Saturn is actually going to go there. So just to recap where we're at. So if you send everything out, we've got the Kuiper belt at one end. Next up, we have Neptune with that next fold. Uranus at the next one, and Saturn at the next one. That's where we're at. So now let's fold the sun end to Saturn. Make a crease there. This is going to be our most massive planet, solar system, Jupiter. And from here, we keep doing a lot of folding and it just gets smaller and smaller and smaller. Things get really smushed together. So let's fold the sun to Jupiter. And this is not a planet. This is the stuff that's between Mars and Jupiter. What's that?
Asteroid belt.
Asteroid belt, exactly. This is our random jumble of asteroids. Pretty tiny stuff. I think if you put it all together, I think it's less than the mass of the moon. I think it's not a lot out there. And then from there, let's fold the sun to the asteroid belt. Any guesses what we're going to put there?
Mars.
Mars, bingo, red planet. And then if we fold the sun to Mars, that'll be home, that's Earth. And then two more folds to go. So the sun to Earth. What's that going to get us?
Venus.
Venus, exactly. And then our very last fold, the teeny tiny one, the sun to Venus. You can smush the paper.
Mercury.
And that'll give us Mercury, exactly. So this model is actually pretty representative. It is actually mimicking the placement of the planets. So obviously you can see things are pretty smushed here close to home. And then we get pretty spread out as we get out to the gas giants. This is always a bit of a surprise for people. I think some people have this impression that maybe the planets are more evenly spaced or different order. But it's fun to do this thing to give people a really very visual representation. So this is home. This is what it looks like here. But obviously we've been finding so many other planets out there. You know, thousands have been found to date, all within the Milky Way, but orbiting other stars. And it's interesting to think about how those solar systems are situated very differently. There's a very different geometry to those. So one of the solar systems that I always like to mention is this one called TRAPPIST-1. This was discovered a few years back, made headlines because it has 7 planets in it. So a pretty big solar system. Some of them are within the habitable zone, which is really interesting that these worlds probably could have liquid water if it exists there. And any guesses how that solar system would stack up with this one? For instance, if we would, hold out this model that we've created, and we had another piece of receipt paper for that solar system, how would those planets compare in terms of placement? Any guesses?
Probably pretty different.
Very different, yeah. How so?
I'd say probably a lot bigger.
Bigger. Bigger, you mean more spread out?
More spread out and just overall a bigger
Overall.
radius. Yeah.
Yeah, the
Both.
planets themselves would be larger too.
Yeah.
Any other guesses? So a surprise, perhaps, is that if we took those 7 planets of the TRAPPIST-1 system and we plunked them down next to this model, they would all be within Mercury's orbit. So these things are smushed super, super close to their host star. And that's interesting to think about, is that totally different, much, much closer to the host star than our system. But one of the reasons why perhaps that is has to do with how we're finding these things. So with the case of the TRAPPIST-1 system, the technique we were using was transits. So that is the concept that, you have your bright star and you have your little planet going in front of it and it's blocking some of the light. So we're seeing that dip in the light. And that technique, it's easier to see that technique if the planet is closer to the star because it's blocking more of the light. If the planet's, way out in front of it, then you're just blocking a tiny bit. So it's more of a selection effect that, we see this system because it is so close to its host star. So it's kind of, we're selecting to see those kind of solar systems. So that of course raises the question is, are there things out there that look like our solar system? We just haven't seen them, that we just don't have the detection technology to pick it up. That could be very true. And then there's another solar system that was recently in the headlines. So these are planets orbiting Proxima Centauri, so our nearest star. And this one was exciting because I think it was just a few weeks ago, there was a 3rd planet found orbiting the star. So we knew of 2 in the past, and now we have a 3rd one. And this one, like TRAPPIST-1, if you were to plunk it down in your model, would still be within Mercury's orbit. So again, really, really close. But again, that's probably because of how these things are found. So what is another way of finding planets? Is this something that you've maybe talked about in club, or, have you talked about how astronomers actually do this?
I know one way to find planets to carefully analyze the gravitational
Yes.
forces that they have.
Exactly. So that's actually this technique that was used to find the planets around Proxima Centauri, the closest star. So the technique is called radial velocity. So the idea is that as a planet orbits around its host star, because of gravity, there's gravity both ways, the planet is obviously moving a lot, but the star itself is also moving. So it's kind of wobbling back and forth. And astronomers can actually detect that wobble. So if they see that this star is moving, even if they can't see the planet over here, they can infer that something is going around the star, which is really cool. And obviously, if you have a bigger planet that's closer in, it's going to tug more on its star. That star is going to move more. So again, it's really based on how good our technology is. In the future, if we have better technology that could detect smaller planets farther away, maybe we'll see more of those. But for now, we're kind of biased towards seeing the stuff that's really, really close into the star. So that's basically how, was there a question?
Yeah. So in the event that there's multiple planets, would there be any involvement of the Fourier series in that situation when trying to infer the planets because of gravity?
Yes, so absolutely. When you have multiple planets, it gets complicated because you're basically trying to disentangle all these different signatures of multiple planets. And it's not as easy as saying, oh, this is the signature of planet A and this is the signature of planet B. They overlap, they interact. There's absolutely, that's where the math comes in, the computer science comes in, the modeling comes in to try to figure out how this works. And it's hard because we obviously don't know to begin with how many planets we're looking at. Are we looking at 4 planets? Are we looking at 7? That's where the modeling really plays a huge role. Yeah, good question. So that's the basic gist of, I just wanted to kind of convey how what we're seeing is A, very different from what we know, but B, how that really probably depends on the technology that we have right now. So that's where, as an astronomer, we are so dependent on the people who, build our telescopes, who build our instruments, the people who do the engineering, the people who do the physical fabrication. That is so critical to what we're able to conclude as scientists. So I really like to play that up because people sometimes tell me, oh, astronomy is really neat, but I don't necessarily want to be an astronomer. I like to build things, I like to construct telescopes, and I tell them we need you. We absolutely rely on your skill set. So please, study engineering, study material science. All of that is so extremely useful. So maybe that's some of your interests as well.
Or study journalism, because
or study journalism. That's
the
good
public,
too.
the public
Yes.
loves this stuff.
Yes, indeed. Well, I would love to open it up to general questions. Happy to chat astronomy science, happy to chat career paths, anything that would be of use to you. I am at your disposal.
You
Well, I'll
probably
start. Go ahead, Drew.
okay. You probably know this, but I honestly don't. Why is it that our solar system is so expansive compared to others?
Oh, excellent question. I mean, there's so many ideas that actually in the past that our solar system looked a lot different. So that some of the gas giant planets were actually closer in, and then there was gravitational interactions and some of them were booted out. So it's more the idea that our solar system as it looks now is not how it's looked since its beginning, that things have gotten jumbled up. I don't actually know if maybe there would be another one of those episodes of movement in the future. If some of our gas giants would get jumbled or ejected.
Yeah.
I don't actually know, but it could change again.
That's interesting. That's really interesting.
I know in the activity, it seems like all the planets are twice as far out as the last one.
Yes.
Do you think that's a coincidence or?
I think it is. I don't, there should be obviously no reason that there would be a certain structure. I think that's just the way it kind of happened to be. And,
do you know
obviously,
if it's the same with their masses? I know in general they get larger, but
I don't think that scales with the masses. I'm trying to think off the top of my head.
Yeah.
Yeah, I
Okay.
don't think so. But no, I'm pretty sure if you labeled each one of these with their masses that you wouldn't see the same trend. I don't think so.
I have a quick question about, so it's mostly about the size of this might be too small, but roughly how large would the planets have to be on this scale?
Great question. Minuscule. So let's see, I have worked this out. I mean, if you were sketching these things, the inner planets would be far smaller than a pencil dot, for sure. I think a fair bit smaller than that, actually. So yes, if you were making a true model that had the actual distances relative to their sizes, you would barely see the planets on here. Yeah, tiny.
Okay, I have a question. So you mentioned 2 methods of detecting exoplanets, one of which is the transit method. Now, I just want to take a quick time out there, Kathy, and tell these students, some of whom know this, but many probably don't, that a regular volunteer for our club and for young astronomers statewide is a man named Ken Hose, who you know. And, we haven't done the Pine Mountain Observatory trip in 2 years. And so remember, 2 years in a high schooler's life is an eternity. So while we did that for many years and it had a great tradition, we haven't done it for 2 years. And we may or may not do it this summer. Ken's up for it and I'm up for it, but so far no one else is of our mentors. And one of the things that Ken does, he does many things, but one of the things he does with youth who go study with him at the Pine Mountain Astronomy Camp is he chooses a exoplanet system that he knows that's been discovered already by NASA or whomever. And then the students spend the week learning to use his equipment, and they actually gather data that shows the transit.
That's
So
really
that's pretty cool. So Ken doesn't discover exoplanets, but he does discover, or measure maybe is a better word, the orbital parameters of these. Because when these were being discovered by space telescopes, Kepler Space Telescope or whatever, the main objective was to discover them. They didn't have time to make measurements. So Ken is doing real science that he then publishes. And in fact, a lot of the work on exoplanets is done by serious amateurs like Ken. And Ken has told me that whether or not we're able to pull off the astronomy camp this year, he's happy to work with students who can either or both take a trip out to his home observatory, which is in Wilsonville, it's only half an hour away, or do it entirely online. So this is just sort of an advertisement to any of you out there listening who not only don't know Ken, but you might not even know students who've worked with Ken in the past. Normally, Kathy, I relied on the students to pass this along, but we have a break in the chain. So if any of you are interested in working with Ken between now and August, let's say, maybe even September, and doing some astronomy where we make measurements, measuring the orbital parameters of exoplanets and even learning what that phrase means, make sure you talk to me. Because Ken's retired and he loves to do this and he loves to work with young people. So that was an aside. So the transit method, and then you mentioned a second method. Would you mention that again for me?
Yes, so that is called radial velocity. So this is the gravitational one where the planet, which we don't see because it's so tiny, as it goes around the star, it's tugging gravitationally on the star moves back and forth.
Okay, so you're seeing it through its effect on gravity. The star is effectively wobbling.
Yep.
Are there any other methods that are either being used or maybe proposed to be used? Or
yes, so those two, the transit and the radial velocity, are by far the most common. They are kind of the workhorses, that I think probably, if I had to guess, 80 to 90% of the known exoplanets have been discovered in one of those ways. I think those are the most common. Trying to think of what else there is. I mean, there's direct imaging. So in very, very rare cases, if the planet is close enough to its star and basically emitting enough infrared radiation, so it's glowing enough, you can actually image it directly. So you literally take a picture on the sky and you're like, oh, that's the planet. But that's very rare. Because again, you need a planet that's super, super close to its star and you need something that's relatively big. So that's rare.
Here, I don't know that what I'm about to say makes any sense, but I'm going to predict that in the future, there will be more different ways to detect exoplanets as our telescopes and data analysis procedures get better. And who knows, maybe some of these students will be on the forefront of that.
Okay.
And I'm going to hog a little bit because I have a second follow-up question and kind of just let the students know I'm a little embarrassed. A teacher's life is very busy. I learn it's a great busy, it's good busy, I'm happy, but I learn all my new stuff during the summer. And there's been so much about the James Webb Space Telescope in the press that I have barely read the headlines. And I know, though, that at least part of the mission of the James Webb Space Telescope is to improve our detection of exoplanets. But can you tell us more than that?
Yes. So big picture here. So the James Webb Space Telescope is kind of the successor to the Hubble Space Telescope. So like Hubble, it is outside of our atmosphere, which is great. You know, it's far away. It can really peer much further into space. It doesn't have to deal with all the blurring effects of our atmosphere, which is a good thing. So basically, yes, this telescope is big, has a big mirror. It will be sensitive to infrared light, which is a really interesting wavelength because there's a lot in the universe that emits infrared. And yes, we are extremely excited that it's really going to help us understand exoplanets, specifically their atmospheres. And atmospheres are interesting because there's obviously a whole slew of chemistry in an atmosphere. And by looking at that chemistry and trying to find particular elements, we can try to figure out, is this a place where life could exist? You know, could life have a toehold on one of these worlds? So by looking at particular signatures, you know, oxygen, nitrogen, you know, whatever else could be in a habitable atmosphere, we can get a sense of if life could be there. And that's something that we've very rarely done before. We just didn't have a telescope big enough, sensitive enough to do that. So astronomers are really excited for this one.
Thank you.
It looks like we have a couple of questions from the chat.
Yes, go ahead.
Ryan asked, what are the parameters for a planet to be in the habitable zone?
Oh, fantastic question. So the habitable zone is kind of this imaginary sphere around a star. So basically, you're not too close to the star. If you're too close, it's going to be too hot. Any water that you have, and we assume we need water, is going to boil away. It's not going to be there. If you're too far away, any water that you potentially have is going to be frozen, locked up. And we think that life likes liquid water. You know, oceans are a great place for life to develop. We think that's how things got started here on Earth. So basically, the habitable zone is that special distance from the star where you can get not too hot, not too cold, you can have liquid water. And then let's see, I see another question, a question about being a science journalist. Let's see. Oh, these are all great questions, Gavin. So I'll start a little bit with, you know, how do I figure out what I'm going to write about? That's a great question. And so I'm a freelance science journalist, which means that I don't write for one particular magazine or newspaper. I get to write for all different ones. So I kind of decide what I want to write about. You know, I try to talk with as many scientists as I can. I hear about what's current research. And then I have to figure out, is this something that the public would care about? You know, is this important? Is this newsworthy? So it's a lot of kind of trusting instinct, but then also chatting with scientists and asking them, is this important? So kind of truthing it that way. And in terms of, so another question was, do I work from home? Do I travel? I do a lot of work from home. So even before COVID, I was camping out at home. It's nice because I do have a lot of flexibility in the sense that I need an internet connection, I need a working phone. But basically, if I have those two things, I could pick up and move and go somewhere else and still do my job. So that's pretty neat. I do get to travel sometimes. I wish I could travel more at the moment. But if I'm working on a story that is, you know, either a big story, meaning that it's, you know, it's something very newsworthy, it's a long story that would appear in a newspaper or magazine, sometimes I do get funding to actually travel. And in that case, I would go and visit scientists who are doing the work. It's really neat. It's very special to be able to travel. I feel like that really makes the story come to life. And a couple of years ago, I was lucky enough to take a big trip. I was able to go to Taiwan, which was a really amazing experience. And I was going with scientists who were studying landslides. So they were working in a national park in Taiwan studying landslides. And I got to go with them for a week. And I got to hike around this park and take a ton of notes and ask a ton of questions. So for me, that was a really, really cool experience to be able to do that. I don't get to do that for every story, of course. Most of my stories, I just interview people on the phone, do a Zoom call. So it's not quite as exciting, but I would love to do more of those. And then let's see, and then process for writing an article. Oh, I see that Joe has just pulled up my story. Yes.
So I couldn't resist, Kathy. By the way, Kathy has a website, KatherineKornei.com, where she has some of her latest articles. I wanted to say the New York Times article really intrigued me. However, I have let my New York Times subscription lapse, but I read it a lot. So I've reached my limit of free articles this month. So both my wife and I subscribe to the New York Times. So I tend to use her computer a lot to read them. Hers is more active. But just tell us the title of that New York Times article, because that's fascinating.
Which one are you talking about?
The one about the fall of ancient Rome.
Oh, that one. So this was a story that I wrote. Very cool science. So basically, these scientists were looking at ice, and they were pulling out long cores of ice. So big long things, like this size. And they were digging them out from places like Antarctica and Greenland. And by looking at the chemistry within the ice, they could actually figure out when a volcano erupted, which is, I think, pretty amazing. So basically the idea is that a volcano erupts, it obviously spews a ton of stuff up into the atmosphere. That stuff eventually rains back down. And if it lands on snow, it's compacted into ice. So by looking at chemistry of ice, you can figure out volcanoes. It's amazing. So what these scientists were doing is they were figuring out volcanoes that were linked to certain periods in history where there were big changes in terms of falls of empires. And volcanic eruptions can have a huge impact. They can change the climate. They can make things colder usually. And that can really change a society. So the idea was, by linking these signatures of volcanoes with big historical changes, you can say that something that happens on Earth, a natural disaster, is changing a society, which I thought was amazing. So that was really fun. That was a big story I wrote.
Yeah, and there's another one that is linked on your website on the Taiwan landslide experiment, which is very interesting. I don't know that you know this, Kathy, but I teach at Ida B. Wells High School. Physics is really my career, but I teach earth and space science. And the astronomy club is space science, but actually right now I'm teaching earth science. And we do something called Climate Change Fridays, where we talk about climate change and have guest speakers every Friday. We just started that because we just switched to the new semester. I have not yet read this article on the landslide effect, but I will, and we might work that into our curriculum. Anyway, I kind of interrupted there, but I wanted folks to know that they can go to Katherine Kornei, of course, .com and learn more about being a journalist. I'll stop sharing. Were you still talking about answering Gavin's questions, or did you get to
Let's see, let me look at the chat, see if I missed one part of it. So process for writing an article. Great question. Obviously, I need to figure out, what is the current science being done? What is the new results? And why would the public care about it? So that's always the big question of, how do you make this relevant to somebody's life? How do you convince them that they should care, that they should read the story? So I do a lot of talking with scientists. I interview a whole lot of people. I read original research. So I get, a subscription to a journal, and then I actually read the original paper. So I understand all the nitty-gritty science details, which is important. And once I've drafted a story, then I work with an editor. And my editor, gives me comments. They're the ones who read the first draft. They figure out, does this make sense? Would our readers like it? What questions do I have? So just like whenever you write a paper, sometimes you go back and forth and you make changes and revisions, and hopefully you make something better at the end. And then I also get to find images, which is fun. So I get to ask the scientists of, do you have any cool imagery to go along with this? Maybe I have a picture of them working in the lab. Maybe I have a picture of them doing field work. So again, I try to make the story come to life with cool images too.
And not to embarrass you or put you on the spot, but have any of your articles won any awards?
Yes, yes. So I've won awards as a journalist. Yes, and that's always fun to really feel like I'm doing something that people are A, reading, and B, caring about. I've also won some fellowships, which is really fun. Those have let me go to certain places. So, for instance, going to Taiwan was a fellowship, and I had another fellowship where I went to a oceanographic institution, and basically hung out with scientists for a week who were studying all things ocean related.
Kate Latimer, are you there?
Yes.
So Kathy, again, not to embarrass Kate, but we have a second award-winning journalist here with us because junior Kate Latimer, I'm trying to share my screen here and I messed up. Can you guys see my screen?
Yes.
Where the heck did it? Oh, there it is. So Kate, tell us a little bit more about how this article came to be and the award that you won, Kate.
Okay, so last year I initially wrote an article about just kind of the basics of like dark sky and light pollution. And I interviewed Mr. Minato for it, and that kind of got me into the whole dark sky and light pollution vein, really, of astronomy club. And so this year I decided to rewrite the article a little bit with my new knowledge and yeah, just like a little more experience and all that stuff. And yeah, so I submitted it to the Scholastic Art and Writing Awards in Journalism. And I got a gold key, so now it's going on to the national level. So we'll see how it does.
Congratulations.
Yeah, thank
That's
you.
really neat, really neat.
Kate,
Have
I know
you-
you're good in all your classes, but are you considering a career in journalism or writing? Is that your favorite?
Yeah, I definitely am. I'm kind of between doing a more creative writing path or a journalism path, but I'm gonna do one of those.
Wonderful. Hey, did you get a chance to visit any of the dark sky sites? Have you been to those?
I actually have not yet, but I fully intend on doing that in the future.
We're going to do that together once COVID allows us to. Kate and I and the rest of the Dark Sky group.
Nice, nice.
Well, now you know, Kate, that you know a real live person here who's earning her living as a science journalist. Yeah, that's great.
I know, that is so cool.
Back to the chat. I kind of lost track. Brandon, are you following? Are there any more questions there?
I'm following along a little bit. Adam asked if you travel for work, and if so, how often?
So I typically go to science conferences. So that's where I hear a lot about new research. So I try to go to 2 to 3 of those a year. Most of those are within the US, pretty local, but I have gone international. So I have gone to a conference in Europe that was really fun. So I go to those, and then if scientists invite me to come and visit their lab, then I might do one of those visits too.
And Kate also asked how you go about turning scientific concepts or breakthroughs into articles that are accessible and easy to understand. For
a lot of practice, Definitely. I try to think about, how would I write something that would be interesting to somebody who's not a scientist? So I might try it out on a friend, and kind of think about what are they interested in? What do they care about? And how can the science be made relevant to their life? And sometimes that's really hard. I'm writing about something that's relatively obscure. And so I think I don't hit 100% every time. There are definitely some stories where I feel like I'm connecting more with readers, that I'm really putting something out there that people care about. And sometimes it's maybe a little more of a stretch. So I think it's good as a journalist to be humble about that I'm not perfect every time, but I try, and I really rely on my editors to give me good feedback too. That's really helpful because they know what their readers like, so that they can offer me advice of, try this differently, make this analogy. Here's how you can make your story stronger.
And then Marina asked if there's like any specific type or area of science that you write about more often, if you kind of cover everything.
Oh, I would say mostly earth science these days, which I think is fascinating. I love the idea that you can go and do field work. You know, I love the idea that you can go and study a glacier. You can send a vehicle to the bottom of the sea and learn that. And obviously our planet is our only home. So I think it's really critical that we understand it. It's important that we protect it. Climate change is a big thing these days. You know, so that's something I certainly incorporate into a lot of my writing. But I also try to be positive. You know, I try not to make a story all doom and gloom, just saying, you know, we're you know, this is horrible, we're going down the drain. I do try to offer up some note of something positive, that some action that people can take.
I just have to jump in there again, Kathy. One of the things that makes me very sad, by the way, in climate change, we always start each lesson with climate change good news.
Good news, that's important.
So we started last week on Climate Change Friday with the hole in the ozone, which how it was such a horrible problem, and then the whole world came together and trusted the science, and every country in the world signed the Montreal Protocols. And when we put our minds to solving a problem, it's not totally solved, but it's on the way to being solved. So we do start with good news, because, you know, bad news, too much bad news just makes you depressed. I wanted to point out, in case you're not looking, Marina is a sophomore in my earth science class. And I was really hoping you'd come, Marina, because Marina shows a lot of enthusiasm and excitement for earth science and a lot of positivity, and I wanted her to meet you. So you've met now.
Yeah.
But here's the bummer thing. There are 7 or 8 high schools at Portland Public Schools. And of these traditional high schools, not the specialized programs, Ida B. Wells is the only one that offers earth science.
Really? That is
And-
surprising. Wow.
And do you know why we offer earth science?
Because you teach it.
Because I am an easygoing, pleasant person, but I have to throw a fit every year
Wow.
and say, we have to have earth science.
Yeah.
And we're also the only Portland Public School that teaches astronomy.
Really?
The real move has been physics, chemistry, biology, which of course, I'm a physicist first. I love physics, and I certainly love chemistry and biology, though I know less, but sometimes the allied fields that pull all of those together, like earth science, astronomy, archaeology, and things, really excite kids. So I've been, in my old age, I'm trying to convince the school district to offer more of these electives.
Absolutely.
There are a lot of kids who love earth science.
I wish my high school did not have actually either earth science or astronomy. I wish they did.
Yet you made it into
Yes, I did.
I'm
still
good.
study.
Do you put all of your articles on your website, or just the most recent, or what?
I'm pretty complete. So if you look at my website, I have a link called Portfolio, and I stick just about everything there.
Okay, I'm going to pick out the most appropriate article for earth science, and we're going to have a Kathy Kornei assignment in earth science class. So I'll let you know when that is, and
I would love to come and chat about it.
which article. We should wrap this up pretty soon, but I see Caleb has one more in there. We can always count on Caleb for great questions.
I just want to
Read it out
clarify
loud,
the
Caleb?
question. Oh, okay, yeah, sure. So all right. So I've seen a lot of popular science articles, and not like the magazine in particular, but just the genre of popular science, where the articles will report on a scientific issue or phenomenon and make it sound a lot more immediate or cutting edge than it actually is. Do you think that's a widespread issue, and what's your experience with that phenomenon like?
I think it is a widespread issue. I think a lot of things out there are clickbaity, you know, that there's kind of this draw to make people click on something for advertising dollars. And I think that's a sad situation. It's also hard because I know that publications, newspapers, magazines need to make money as well. So I get that. I think as a journalist, my perspective is that oftentimes when I write a story, the headline that I suggest is not always the one that actually gets used. And that can be frustrating because oftentimes my editor will change a headline a little bit to perhaps make it a little more clickbaity, a little more, draw people in. And that's hard. Sometimes I get frustrated. Sometimes sometimes something is written that I don't agree with, and then I will write back to my editor and say, no, we can't use that. That's too much of a stretch. So I try as a journalist to rein in my editors when they get too clickbaity.
Thank you.
All right, I think we have one more question, and it was from Ryan, and it was about, do any of your articles ever get like censored, or do you have any problems with the politics surrounding your articles?
No, thankfully, I have not had anything censored. I've definitely had I've written some things that were maybe a little more liberal leaning. I wrote, for instance, an article about a transgender athlete. And I remember that there was some coverage I found online of conservative groups that were not happy that I had given that subject coverage. So I think there were some articles written of like, why is she covering this? This is not worth coverage. But I try not to let those things bother me. I'm proud of what I do, and I'm really glad I got that story out there. And there are certainly cases where not everybody's going to agree with what I write, but I believe that what I do is motivated by data. I'm following the data, I'm putting the science out there, and hopefully people can agree that the science is sound.
Amazing, yeah, that's good to hear that not a ton of your work has been
No.
shut down. That's really good to hear. But other than that, I think that's all the questions we have. Everybody who's able to, go ahead and turn on your microphones or your cameras, and let's give Kathy a round of applause for an absolutely amazing talk.
Thank you.
But yeah, if there's no other questions, you guys are free to go. Thank you so much for coming, Kathy.
Yeah.
Thanks, Kathy.
Good
Bye.
night. Bye.
Thank you.
Thank you.
Thank you.
Bye. Thank you.